Thanks for the kind introduction, and it's great to be here. I'm on this tour through the Midwest. I'm from Ohio originally, so it's kind of a bit of a homecoming. Although being in California for almost 12, 13 years now, my blood is thin, so it feels cold today, even though everyone's been telling me how great the weather is. But today I thought I'd tell you a little bit about a project that sprang up about 5 years ago. In my lab for a long time, we've been interested in the role of fluid mechanics in different biological systems, mainly in swimming and flying. And along the way, we found that there's some interesting ways in which nature, in the case of fish schools or seagrass, like I'll talk about today, have solved some challenging fluid mechanics problems for us. Of course, the challenge is for us to figure out exactly what that solution is and how we can use it. And so today I'll talk about the application to the problem of wind energy. Now, broadly speaking, our goal is to develop wind energy technologies that can match the reach of the wind. And to give you a sense of that wind resource, here's a global wind map. The current, the total power available in the wind today is about 20 times global energy consumption. So it's enormous. And if you look at this map, the colors in red, yellow, and green, these are places around the world where that energy is sufficient to generate useful electricity, for example. And so with very few exceptions, heavily forested areas like the Amazon, the Congo, and Central Africa, some parts of Southeast Asia, the wind really is a global resource. But despite this global reach of the wind, and despite the fact that it's a large resource, and also in spite of the fact that in the popular press people talk about wind energy as a mature technology, the fact is today only 4 countries get more than 10% of their electricity from the wind: Spain, Portugal, Ireland, and Denmark. Germany's right at about 9%. Here in the US, we're still under 4%. I think what's maybe even more tragic is that there are developing countries like Somalia, Malawi, that have excellent wind resources, but some of the lowest electrification rates in the world, with fewer than 1 in 10 people having access to electricity. So the question we ask is what we as engineers and scientists can do to change this situation. Now, ultimately, it comes down to costs. If the technology is less expensive, it's more easily adopted. And the most important parameter in this context is what's called the levelized cost of electricity, the cents per kilowatt hour of energy. I won't focus on that today because it requires some assumptions about system lifetime. Will that set of wind turbines, for example, last for 10 years or 15 or 20? Also some assumptions about operations and maintenance. And so a parameter that's closer to the physics of the problem is this capital cost of electricity. Essentially, how much money are you putting in to build the system, and what's the average power produced? And so our goal is going to be to figure out ways to maximize that denominator. Now, that denominator in turn is the function of 3 parameters. First of all, how much wind power is entering that farm. Secondly, the turbine swept area. So how many machines can we actually fit within that area to interact with the wind? And thirdly, the power conversion efficiency. So of the energy that interacts with those wind turbines, how much of that can be successfully converted to electricity? Now, the problem I see is that over the past 30 years, since the last real energy crisis, most of the focus has been on this third part of this equation, the conversion efficiency. And so people will think about, for example, the comparison between the standard energy generation device today, the horizontal axis wind turbine. Today I'll be talking about vertical axis wind turbines, so they're rotating on this vertical axis. And today we'll typically be comparing large turbines versus small ones, but the general question people will ask is what fraction of the wind energy flux through that swept area can be converted to electricity? And invariably, it's the case that horizontal axis turbines individually tend to be more efficient than vertical axis turbines today. Now, part of that issue is simply that we don't yet understand fully the unsteady aerodynamics of the vertical axis wind turbines. But today I'm not going to try to change this equation, but rather to demonstrate that this is actually not the most important piece of the puzzle. But nonetheless, before we get there, it's useful to ask, theoretically, what's the maximum fraction of energy that you could produce from one of these systems? So this was a problem that was considered by Albert Betz in the early 20th century. And so you can do a simple analysis. Imagine that this is our wind turbine. You have wind coming from upstream at U naught, an area A naught, and then leaving at a slower speed in a bigger area to conserve mass. Now the power is going to be the mass flux through the system times the difference in kinetic energy upwind and downwind. Now the assumption he makes, and it seems to be a reasonable one, is that if this flow around the arc here is steady, so you don't have time-dependent fluctuations, then the velocity u1 is approximately the average of the upwind and downwind flow speeds. And so what that allows us to do with a little bit of algebra is to show that the maximum power extracted is 16/27, 59.3%, which is now called the Betz limit in his honor. So we can ask, how do turbines do today? So on this vertical axis, I'm plotting the efficiency. Here's that Betz limit. And in green here, this is an average of modern horizontal axis wind turbines. In fact, this plot is a few years old. I'm plotting against tip speed ratio, by the way, which is the ratio of how fast the tips of the blades are spinning relative to the wind speed. And so today, even above 50%, you can get performances above 50%, which is starting to encroach upon the efficiency limit here. So the situation in wind is very different from, say, solar energy, where today PV cells, for example, there's still a lot of room for improvement before you get to the theoretical limit. In the case of wind turbines individually, they're approaching the theoretical maximum. And so this is one of the reasons why people say wind energy is mature. And so the question we can ask is there fundamental room for improvement in this field? Excuse me. I've been talking too much. So what we're going to do is have a different starting point and look at those first two terms in the average power produced, the wind power into the farm and the total turbine swept area. And we ask a different question, which is what fraction of the wind energy flux into a wind farm can be successfully converted to electricity? And that's going to turn out to give us a different answer. Now, to orient ourselves, there's a couple of parameters we're going to need. First of all, the idea of a frontal kinetic energy flux. If you were to stand at the front of a wind farm and the wind's hitting your face, that's essentially this resource. It's proportional to the cube of the wind speed. And as I've illustrated here, the wind speed tends to increase with height due to friction with the earth, and these arrows illustrate that. It also depends on the area, the frontal area of this wind farm. But there's a second source of energy for wind farms that has only really received attention in the past few years, which we call the planform kinetic energy flux. This is the energy that's introduced due to turbulence in the field. It's proportional to the mean of the wind speed, but also due to Reynolds stresses or turbulent fluctuations. So U prime are fluctuations in the streamwise direction through the farm. W prime are vertical fluctuations in the velocity. And so this planform kinetic energy flux is going to be the main player in the story that I'll tell you today. First of all, we know from recent work at Johns Hopkins, for example, that this is the primary power source in large-scale wind farms. That frontal kinetic energy flux is actually exhausted after the first few rows. And so the downwind turbines are primarily getting their energy through this source, the planform kinetic energy flux. Now, I would also argue that this then becomes the more important limit as opposed to that Betz limit for individual wind turbines for a couple of reasons. First of all, that Betz calculation said what the maximum amount of power was that we could extract from that swept area. It says nothing about what happens to that leftover power. And as I'll show later on, there's ways in which that can be extracted as well. But another way to look at this issue is if you imagine a front view of your wind farm, and here in the circular sweep, you have the efficiency reaching about 50%. But in between the turbines, essentially your efficiency is zero. And so we would argue that rather than spending lots of effort to get from 50 to 51 to 52%, that we should do something about the big zeros in between the turbines. Now, let's quantify that planform kinetic energy flux. We can get at least an order of magnitude estimate by using some standard models for the atmospheric surface layer. So imagine you have the wind profile over the turbines. And so if we assume it's a logarithmic profile, we can estimate that Reynolds stress term using the von Karman constant, which is about 0.4, the concept of a zero plane displacement, which simply says that if there were no turbines there, we would expect the velocity to go to zero at the ground. Because of the turbines, it's actually elevated a bit. And so rule of thumb in canopy flows is that it's about 2/3 the height of the structures, in this case, the height of the turbines. And then the roughness length. This is essentially a characterization of how smooth the surface is. And without the turbines there, you get a small value, but with them, it can be increased to something on the order of 1/10 of the height of the structures. So we can plug these numbers in, and you'll find that in 8 meter per second wind speeds, which are typical for a wind farm that might be here in the Midwest, for example, the energy flux through the top of the farm is about 68 watts per square meter. So the question we want to ask is, how does that 68 watts per square meter compare with current wind farms? So on the next plot, I'm going to show you, it's a bit busy, but I'll step you through it. This is from a nice book by David Mackay, analyzes various types of wind energy. On the vertical axis, it's showing the wind energy consumption per person in different countries, so it's kilowatt hours per day per person. And on the horizontal axis on a log scale, it's the population density, how many people per square per square kilometer. And so, for example, Singapore is a country that has a very high energy consumption and also a very high power, a very small land area, so it has a high consumption in terms of power density. A developing country like the Sudan, as you might expect, has relatively low energy consumption, also has a big land area. Now, the thing that should alarm you are these tails. These are the 15-year changes for a lot of these countries, China, South Korea, India. So the populations are increasing, but they're also consuming more energy as their quality of life improves. They grow their middle class. So the nice thing about plotting this on a log scale is that these lines of constant slope have units of watts per square meter, that metric that we talked about on the previous slide. So for example, concentrating solar power using mirrors to focus the sun's heat and running a thermal cycle, for example, will give you about 20 watts of power per square meter of that solar farm. Biofuels, energy crops, they'll give you about half a watt of power per square meter of land area that's dedicated to that. And here's wind power. This is the modern wind farms today at just about 2.5 watts per square meter on average. So one repercussion of this is that, for example, look at South Korea. It sits above that line, and so you could take modern turbine technology, cover the entire land area of South Korea with wind turbines, and still not produce enough energy to satisfy their needs. And so from a research perspective, our goal is to take these curves and push them to the upper right. Now, you'll see, remember on the previous page, we just calculated the planned form flux going into the wind farms, and you can see this performance gap, 68 watts versus 2.5 watts here. So there's this interesting paradox, it seems, whereas the individual wind turbines are approaching the theoretical limit of how effective they can be, wind farms as a whole are performing much worse. And so you might ask why that is, and I think this picture here explains it very clearly. So this is in the North Sea, an offshore wind farm, and it is a picture taken on a day when it was, there's condensation here. So you can see the turbines in the front seeing a clean air, but each of these turbines creates a turbulent wake. And so all of the other turbines in this wind farm, instead of seeing a smooth air that they were designed for in the numerical simulations and the wind tunnel experiments, they're seeing this very unsteady flow. It reduces the efficiency of their energy conversion. It also reduces the lifetime of the turbines because of fatigue loading due to the constant buffeting from the turbulence of the upstream wind turbines. Now today, the best thing we know to do to ameliorate the problem is simply put the turbines as far apart as possible so that their wakes have less interaction. But that leads to the case where now we have no energy extraction from these regions between the turbines. Now, the problem is not just fluid mechanical. You know, our interest is in fluid mechanics, but what's interesting about the wind energy problem is that there are other issues that will ultimately lead us to try a different approach that I'll tell you in a moment. One of them has to do with the size of these very large structures. So this is a scale drawing of something that would be on the order of 3 megawatts, a utility pole, a transmission tower, a forest tree. So these structures are enormous. And for the engineering, the loads scale in such a way that you'll need more materials for the tower. The types of materials that are available to be able to withstand the gravitational, the centrifugal, the wind loading for these very large blades means that you're limited in the types of materials you can use, and ultimately that can increase your cost. Installation and maintenance. So I've seen this actually on a few occasions as I've been driving through the Midwest here. To transport these, the limitation now on the size of the onshore wind turbines in the US is now our highway system, getting these underneath our overpasses. So the logistics become more complicated, and although you can imagine doing things offshore, you have to imagine now that these are on floating barges going to that offshore site. If you want to maintain them, you have to use helicopters often. And so again, these things can increase the cost of the energy. Now there are aspects that you might say are pretty subjective. I actually think these wind turbines look really cool, but a lot of people, or if there's even a few people who disagree, then that can hold up permitting processes. There's a very notable project in Cape Cod that for 12 years now has been trying to be installed, but due to objections about potentially obscuring the sunrise or other things, hasn't happened. There's other concerns about impacts on birds and bats, the signatures, visual, acoustic, and radar. This third one, in fact, has led even the federal government through the FAA and the military to shut down certain projects where they're concerned about their radar being interfered by the sweeping blades. And then lastly, access in the developing world. Again, think back to that plot I showed you, these countries that are increasing their energy costs. The fact is, even if you gave a place like Somalia free 3-megawatt turbines, they wouldn't have the infrastructure to deliver that energy to their communities. So for all of these reasons, we've decided to try a different approach to the problem, which we think can be complementary to these turbines, but frankly, go many places that the large ones can't. And so it's the idea of using many smaller and vertical axis wind turbines in order to generate the power. So it potentially addresses all of those issues we just talked about with smaller structure sizes, materials costs, and wind farm signatures. They're very simple. So these vertical axis wind turbines can take wind from any direction. So you don't need a drive to point them in the direction of the wind. At this small scale, they don't have a gearbox. They're just a direct drive system. So it's a very simple system, and that also simplifies installation, operations, and maintenance. I'll show you our research wind farm later on out north of Caltech, where we do most of our operations and maintenance just using a pickup truck. So there's no sort of specialized machinery needed. It's scalable. So if you're a rancher and you need 10 kilowatts of power, or you're a municipality and you want to generate 100 megawatts, the only difference is in the number of turbines. There's no difference in the basic unit of generation. And it's interesting to note that of the maybe dozen companies that are around the world that make these, there's never been a reported bird or bat strike. Now, some of that's due to the fact that they're closer to the ground, so the birds simply fly over them in many cases. But also the visual signature of the blades as they're rotating is different from the visual signature of the horizontal axis turbine. And so it's thought that for some animals, they're able to avoid them more easily. Now, let's go back to the power density comparison. Again, that's sort of the meat of the performance metric that we're interested in. So imagine you're looking at a bird's eye view on these turbines. One way you can get that power density is what was done in the book, where you take existing wind farms and you measure the land area, you measure the power they produce, and you get that 2 to 3 watts per square meter. Here we just imagine that we input the rated power, say a megawatt turbine, a capacity factor. Since the wind is not always blowing at maximum, it might only produce 250 kilowatts on average. And then some exclusion zone where we say the other turbines can't be installed, again, due to those wake issues. And we'll imagine it's circular, so you get the 4 on pi there. But let's take a 6 diameter average turbine spacing. That's a bit tight, but typical of what you'd see today. A 30% capacity factor. So these are 2 commercial horizontal axis wind turbines, a GE and a Vestas. And so calculating it in this way, you get the same number in the range of 2 to 3 watts per square meter. Let's look at a commercial a vertical axis wind turbine like one of these guys. The individual units of generation are much smaller, 1.2 kilowatts as opposed to megawatts, but they're also smaller in diameter. And so at the same spacing, so before we've even done a lot of the research I'll describe, we already have an advantage in the power density here. So at equal spacing, we're getting a 350% improvement in power density, and we're using structures 1/10 of the size of the large turbines. Now, that's not to say there aren't some important challenges. Like I mentioned, each of these turbines has a tiny amount of power that it's producing relative to the large ones. So you might ask, can you even get enough of these turbines within the farm to generate enough power and compensate for their smaller size? The second issue may have come to your mind as well. I showed you a plot earlier, a sketch. The wind at 10 meters is slower than the wind at 100 meters. And so the question is going to be whether we can compensate for operation at those lower wind speeds by enhancing the kinetic energy flux into the vertical axis wind turbine farm. So these are the basic questions that we wanted to address. And the approach that we took, as I mentioned earlier, is this idea of studying biological systems. So we've done this in our lab for quite some time. In other contexts, we've studied jellyfish quite a bit for propulsion, looking at the vortex dynamics of something like a jellyfish to inform the design of underwater vehicles that have a longer lifetime, that use less energy. In collaboration with a group at Harvard, this is an example of a project where we use PDMS, a thin polymer film, and we seed it with heart cells from a rat. And with electrical stimulation, you can get it to swim around. And so we took some of what we know about jellyfish architecture in terms of its actuators and some low Reynolds number modeling to demonstrate this idea of soft robotic swimmers. But today our focus is on wind energy, and in fact the inspiration isn't so much jellyfish as it is fish schooling in general. So if you watch the Discovery Channel, you see one of these groups of fish swimming together. They tend to actually have a very regular spacing between them as they move through the water. And if you're not one of the group like that guy, you don't last very long. So we thought that it was interesting that they face a similar challenge. Each of the fish that are neighboring them are flapping their tails, creating this turbulent wake, and the neighbors have to navigate through that wake. It turns out that a fish in this group will, in many cases, use less energy to move through the ocean than it would if it was swimming by itself. And so not only do they sort of handle the turbulence, they actually use that flow structure to their advantage. And so we wanted to see whether we could do something similar. Now, this problem has been studied for quite some time. In fact, there's a seminal paper by Danny Weiss in 1975 where he does some simple point vortex analysis to show that there are certain arrangements, these diamond patterns, if you're looking at from a bird's eye view on the fish school. These are the vortices generated by this fish, for example. And so he imagines that there's ways in which the fish in this row 2 here can actually use those vortices to enhance their performance. And so you get some qualitative agreement between what is computed in these theories and what you find in the ocean. Now, we made a bit of a different logical analogy here where we're saying instead of a fish flapping its tail and creating these vortices, in our case we have a primary wind and it's creating the rotation of these vertical axis wind turbines. Imagine you're looking now from a bird's eye view on the vertical axis wind turbines. And so one of the early conclusions or inspirations was the idea that maybe all the turbines shouldn't rotate in the same direction. You know, if you go to any wind farm here in the Midwest, all the turbines spin the same way. In this case, it actually turns out that the direction of rotation matters in terms of being able to develop a flow through the system at close spacing. Now, we wanted to be able to come up with some quantitative conclusions as to the design. And so we used some low-order modeling to begin. So imagine taking your complex potential. We want to model basically a uniform wind field. We used a point vortex to mimic the rotation of one of these vertical axis turbines, again, from a top view, and a dipole for the blockage. And the benefit here is that if you're interested in 10 turbines or 10,000 turbines or 10 million, that you're just summing over the individual contributions at the different locations of those turbines. So for example, that picture I showed you of the movie of the fish swimming through the water, you can write down something that's, you know, it's at least close form. It may not be so compact, but the actual picture is here. So here's our wind, in this case, let's say coming from the east, or from the west rather. And these are our vertical axis turbines. And so we optimize the spacings, A, B, and C, to try to maximize the amount of wind flow that each of the turbines sees. And so the interesting thing was that the model actually predicted order of magnitude, factor of 10 increase in the power density. So I'm plotting here the rated power. This is on a log scale, so 110 and 100. On the left-hand side, these are hypothetical wind farms using commercially available vertical axis wind turbines in this sort of bio-inspired arrangement. And on the right-hand side are operational wind farms around the world. And so the bio-inspired approach seems to predict this factor of 10 improvement. Now, you could, of course, argue we've simplified the flow significantly by using this potential flow model. And it was for that reason that we wanted to do some experiments to actually test this idea. So this was right around 2009 when the market had crashed. And typically in California, land is pretty expensive, but there was going to be a strip mall they were going to build here. And those plans fell through, so the land was up for sale. And so we bought about 4 acres for $10,000, which in California is a steal. And it also happens to be a nice windy area. So we built a research wind farm here. And so here you can see the turbines. And I like this picture because it emphasizes the idea of a reduced visual signature. You know, if we were using the conventional wind turbines, they'd peak above this ridge line here. And in LA County, that would mean instead of a few weeks for the permitting process, it would be maybe 5 years. So we've been studying the turbines under these natural wind conditions now for about 4 years. This is a video from the summer of 2010. So that's me for scale. You can get a sense of how tall they are relative to my height here. What we did was put a couple of them on some sort of Christmas tree stand legs here. We put them in different positions relative to each other, and we're measuring the actual power being produced under different wind conditions. And you can see how closely spaced these turbines are to one another. So we're trying to really understand how they would interact in these close-spaced configurations. We also have another tower that maybe peaks in the view later there. So there's a reference wind speed that we have for each case. Now the first thing we wanted to do is to study the directional dependence. I said earlier that one of the benefits of a vertical axis wind turbine is it can take wind from any direction. And so now that we're looking at these turbines close together, you might wonder how that would change in this new scenario. So what we're plotting is a normalized power coefficient. This is the efficiency of each of these different paired configurations as compared to an isolated turbine. And so I'm plotting it on a radial plot because I'm plotting the red line is for different wind directions around the azimuth here. So for example, wind coming from the east intersects the circle where CP norm is equal to 1. So basically what this tells us, it's a little above 1, is that at 1.65 diameters apart, these counter-rotating turbines have the same or maybe slightly better efficiency than they would if they were isolated. Now this is in contrast to a 20 or 30% reduction in the performance that you would see in horizontal axis wind turbines at that same spacing. I think more dramatic are some cases like this. This is a statistically significant increase here in the performance of the system at this glancing angle of these pairs of turbines, whereas in the case of horizontal axis turbines at this spacing, you'd see a decrease of 50 to 70% in the performance of the downwind turbine. So dramatically different performance. And then of course, over the 315 degrees that we were able to study, there's relatively limited sensitivity to wind direction and an average of 5 to 10% increase in performance. So again, putting these turbines together can increase the performance as opposed to reducing it. Now, of course, it might be intuitive to you that you couldn't do this infinitely. You couldn't take a bunch of them and cram them into a tiny spot, and that's in fact the case. So what we did next was put a third turbine downstream of those two that we talked about on the previous slide, and you do start to see a drop-off in performance at a downwind spacing of 1.65. So this is the normalized power coefficient here. But if you take that turbine and move it downwind to 4 diameters, you essentially recover the isolated behavior that we had before. So that led us to do a test then where we studied a larger array where all the turbines are 4 diameters apart. Essentially, we wanted to confirm the idea that once you're at 4 diameter spacing for these turbines, it's essentially as if they're isolated. By contrast, current horizontal axis wind turbines, recent studies have suggested they need to be about 15 or 20 diameters apart before they start to illustrate that true isolated behavior. So here's the power coefficient, and I've zoomed in here just to sort of see some difference between them versus tip speed ratio. The point here simply is that if you look at wind coming from the southwest here for these 3 turbines, or all of them, they're basically indistinguishable, and certainly there's no systematic reduction in the performance. So how much power do they actually produce? That's probably more important. So we actually measured the power density at the site. This was over 250 continuous hours that summer. And I'm pegging the measurements to the planform kinetic energy flux, which we measure at the site. We have a horizontal and vertical anemometer. And so here's the data. So it's consistent with the very low order model that I showed you earlier, this idea of getting up to a factor of 10 more power out of that plot of land using this approach versus the existing ones. Now, just to step you through this, first of all, these black dots here, these are mean power continuous. And what that means is if the wind wasn't blowing at the site overnight or for some hours, we just average zeros into the record. So we're taking all of that into account. But just out of curiosity, we also plot what happens just above cut-in wind speed, so only when the turbines are producing power, and you can see an even more dramatic improvement in the performance. Now, you might ask, well, yeah, but that's only 6 turbines. What happens in a larger array? Maybe the wind goes around them. So for the past 3 years, we've been doing larger arrays, and we're up to 24 now. This video's, and this data I'll show you was for an 18 turbine array. And so now we're looking at 18 of these turbines, but you can see the black stumps here. We have 72 of them. So the original idea was we were going to be doing some optimization of the turbines at these 72 different locations, and I'll come back to that. But initially, the first thing we wanted to do was just confirm the performance that you would get of this array over a number of seasons. And so we were also taking wind measurements using an anemometer I'll show later through the center line of the array. So here's the results. I'd like to train your eyes to this side to begin, just to orient you. So first of all, we wanted to look at 2 different types of configurations. One we call a doublet, which is the 2 turbines essentially rotating into the wind. The other, the reverse doublet configuration at the bottom. And you can see the corresponding data for the power density versus wind speed. Now, the open circles are the actual array footprint, and so that data is a little higher than these dots here, which are an estimate of if you had an infinite array, where you might have to then take account of a buffer area around the actual array because you would have more turbines on each side of it. But the point here is really more the order of magnitude of this axis. Again, the 2 to 3 watts per square meter is down here. Even averaged over all the data here, we're 5 or 6 times better. And again, using turbines that are 1/10 of the height of the existing systems. Now, this data is only for when all 18 turbines were running. There's times when either the wind speed is too low for all 18 turbines to run, or at above about 22 miles an hour, for safety reasons, we have to shut down the turbines. And so the rest of this data here shows results when all 18 aren't running. And here you start to see some interesting differences in the two configurations that we think are due to some interesting fluid mechanics that I'll talk about at the close. There's a lot of unanswered questions, and this is an interesting approach to the research for us. We do a lot of basic fluid physics work where we're interested in fundamental units of vortex rings, for example. In this case, we wanted to sort of turn the problem on its head a bit and first figure out whether all of that science was really going to be useful for anything. So we built the field site to actually test whether this idea of getting very large enhancements was real. And now that it is, we're taking a step back and asking questions like, how do the interactions between the turbines, what are the flow physics that lead to that observed enhancement in performance? Because ultimately, that'll tell us how we can optimize the system. So one of the interesting things we're starting to look at is the idea that perhaps there's a suppression of vortex shedding due to the turbine rotation. I showed you in the picture of the offshore wind farm, those very dramatic turbulent wakes that were being created by the turbines. Well, in studies of spinning cylinders, this is from a JFM paper from a couple of years ago, they studied spinning solid cylinders at much lower Reynolds number, but intuitively you can think of this as a low order model of a top view on these vertical axis turbines. Now at low tip speed ratio, in this case it's basically the surface speed of the rotating cylinder to the free stream, you get your conventional vortex shedding. These are vorticity contours here. But once you get above a tip speed ratio of about 1.5, you get a dramatic cessation of the shedding, and now you get a more orderly distribution of the vorticity or advection of the vorticity into the wake. And so one thought is that in these counter-rotating vertical axis turbines, we might have a similar type of physics going on where we're able to suppress the wake such that we can then put turbines closer downstream because there's a faster recovery enabled by this process. Now, this is all two-dimensional, of course, and so one of the things we've been doing in collaboration with the lab at Stanford and what we worked on, I was on a sabbatical there last year, is using a technique called magnetic resonance velocimetry, which gives you three-dimensional, three-component mean flow data. So what you're seeing here, this is a small model, vertical axis turbine flow coming from left to right here, from upper left to bottom right there. And this is an isosurface showing regions of reverse flow, so where the velocity is going basically upstream. And at this point, frankly, it's just a pretty picture. But the idea is to demonstrate that we have tools available to start studying what's the difference between a vertical axis turbine wake and the spinning cylinder, especially at these higher tip speed ratios. Now, as I mentioned earlier, we also do some wind measurements. So this is sort of like our Iwo Jima, raising the flag, except at our wind site. So we have 7 of these sonic anemometers here where we're measuring data to get turbulence statistics at our field site. And so that's been useful to be able to build up a map of what the flow looks like. Again, this is our field site with due north here. Imagine it rotated here. So we're taking measurements along the center line. The interesting thing about this data set, so this is the velocity as a function of your position moving through that center line. And these vertical lines are the positions of the turbine pairs here, here, and here. So you see drops in the velocity and then recovery and a drop and a recovery and so on. And the black line is the field measurements. Using a potential flow model with some fitting, we can actually do a pretty good job of reproducing those results. So even though a potential flow model is lacking the three-dimensionality, it's lacking the turbulence, we can still do a reasonable job of recreating some of the physics there. And so we want to use those low-order models, again, to do optimization of the flow. Now, the other aspect that I won't spend too much time on, but is where we're going, is looking at another analogy. The fish schooling basically told us something about how we might pass the energy through the wind farm in such a way to minimize the negative effects of turbulence. But we also have that planform kinetic energy flux, that vertical flux from the upper atmosphere to the farm. Now, it turns out that in the context of seagrasses, there's also very important mass fluxes that occur for oxygen, for nutrients. And it's been speculated that the sort of irregular height of the stems of a seagrass, for example, actually aid in that transport. And later on, it's been shown, for example, that if you were to take an array of objects all of the same height and you measure the flux that occurs as flow passes through them versus an array of structures that have the same average height, but some are shorter and some are taller, that you get dramatically increased vertical fluxes through that system. And so now, as you can see here, all of our turbines are the same height. If you go to any of the wind farms out here, they're all the same height. But we'd like to look at what happens when you vary the height of the systems, which is something you can do when they're 10 meters tall. You can have some of them be 12 meters and some of them be 18 meters, for example. It's more difficult to do that at a much larger scale. So we've been studying this process. This is some experiments we set up, again, on my sabbatical up there, where we do a low-order physical model. These are spinning cylinders. So this is an array of 10 by 10 spinning cylinders, and we're measuring the flow field through them. One interesting result already is the similarity between the flow field. So this is the horizontal velocity as a function of height for some tree canopy data versus our spinning cylinders. And so in the case of the tree canopy, you get this notch near the height. Here is the height of the tree. So near the crown of the tree, where you would expect there to be a lot of drag, you get this decreased flow. You see something interesting at the top of the spinning cylinders that suggests that there's a non-uniform drag, if you will, sectional drag along the height of the spinning cylinder. And that's something that we're continuing to look at. These studies of eelgrass also have suggested that the typical idea of modeling this as a boundary layer with roughness might actually be supplanted by a simple plane mixing layer model. It turns out that this gets the statistics correct for the turbulent transport in a way that this model sometimes misses. And so we've also been working with a group at Stanford to do large eddy simulation, taking some models they already have for the flow. This is through an eelgrass bed, just stationary stems where you have a single forcing term for the drag. You can replace that with a lift and a drag, a tower drag, so something more complex, but that represents a wind farm. And so the idea here would be to do large eddy simulations of thousands of turbines as opposed to just a few. And then the last bit that is not really related to the fluid mechanics, but is important if you actually want this to show up, in the real world, and that is the manufacturing piece. So one of the potential advantages is that in a conventional wind turbine, you have about 8,000 parts. So let's say you wanted to generate 15 megawatts. You need maybe 12 units of these turbines. Here you need many more units, probably 8,000 of them, but they're much simpler, only needing 12 parts. And so from a volume production standpoint, it could potentially be much more cost effective to make 12 different parts 8,000 times versus 8,000 different parts 12 times. But more work needs to be done there. So on this piece, let me just acknowledge, first of all, a lot of students who've worked on various aspects of this. And again, during a sabbatical at Stanford, collaborating on LES, water channel, and MRV measurements. And just with a couple of minutes, I wanted to tell you about something we've been working on the more biofluid side more recently that we're kind of excited about. So as I mentioned, if you're studying jellyfish and you want to know something about the forces they're creating as they swim, their energetics, it's much more challenging to measure that than it would be for an airfoil that you could put a strain gauge on or mount on a load cell, for example. And so what we've typically done experimentally, those of you who are in experimental fluid mechanics will be familiar with an idea called particle image velocimetry. And this image doesn't show well, but there's tiny beads that we put in the water here, 10, 20 micron size beads. And so we track the motion of those beads in order to get the velocity field around the object. In this case, this is just an elastic plate, basically, that's flapping in a water tunnel here. And so that tells you something about the flow around it, but it's very difficult to get from that data to the forces that are actually being applied in the system. So we've recently developed a code that takes the velocity field and from that gets the pressure field. So here's the corresponding pressure field here. It's in the units of pascals. There's no scaling here. We're just entering the density of the fluid, and we're integrating the equations of motion through the velocity field in a way that reduces or minimizes the measurement errors that are typically associated with these techniques. And so you can very nicely see, for instance, the high pressure as this accelerates forward, so added mass effects versus, say, low pressure in the vortex cores. And so now what you can do is you can integrate that pressure field on the surface and at least high Reynolds numbers, see whether that'll give you an estimate of the forces on the object. So that's what we did. And in this particular experiment, which was done in collaboration with George Lauder's lab at Harvard, we had the force and torque measurements for this particular experiment. And so the comparison is actually quite favorable. And again, this is considering the fact that our PIV is in a two-dimensional plane here, and this is actually a three-dimensional flow. I mean, it's a finite aspect ratio flapping plate. The technique allows us to get quantitative agreement in terms of the forces and the torques on these systems. And so we're planning to use this to study these systems. My reason for showing this is that we have a sort of simple MATLAB GUI that you can download, and so I'm hoping to convince people to try it out on their own data and let us know how it works. So it takes in any velocity field, whether it could be from CFD, but usually from PIV or from magnetic resonance velocimetry, and will compute the time-dependent pressure fields. So with that, I thank you for your attention, and I'd be glad to take any questions or comments. Thanks.